Hi, everyone, and welcome back to episode 8. Today, we're going to be talking about the A register. We introduced or kind of alluded to it in the last episode around this is the first of the registers where they start becoming a bit more complicated. And we spent a little bit of time talking about kind of the control pulses and how machine instructions in the Apollo guidance computer are decomposed into sub-instructions and how those sub-instructions generate the particular control pulses we need to activate the registers and other functions that we'll use in order to operate the computer and eventually run software. So that's something we need to understand a bit more of as we get into the A register. So the A register, if we look at kind of our overall kind of central processor architecture here, is the accumulator, and it's actually the high word of the accumulator. So it works with there's the A register, and of course there's the L register, and that's one we'll talk about next time, which is the low order product or low word for double precision mathematics. So in some math calculations that the computer needs to perform will just be what they call kind of single precision. So those are things that fit into the kind of the 14 or 15-bit word, depending if it's a signed number or unsigned number. But if more accurate calculations are required, both the low order and accumulator are used together to provide additional bit space for higher precision calculations. So part of it, on the kind of the right side of how data is loaded into the accumulator is fairly similar to some of the other registers we've seen. That part isn't where things start getting interesting. It's some of the logical operations that the accumulator kind of does at as it performs some of its operations that we really need to think about. And it actually had me go back and slightly tweak some of the work that I had done on the B and C register. So we'll slightly revisit that and some of the changes that I had to make. First few things we'll notice that it is considered one of the special and central registers. So like the Q register and Z register that we looked at, it is directly addressable as memory, so through this kind of addressable register service, and then it also as the A register through the WA pulse. So let's look at some of the details from the manual to understand sort of how is data written into the accumulator. So there is, of course, the write timer that we use, which kind of mediates when data is written into the A register. We have our WA, so the A register write control pulse, and that's one way that we can use to write data into the A register. It is also, as we said, directly addressable as memory address 0, and that's associated with the WSC control pulse, which is the addressable register write. There is also the read timer, and this is where things will get a little bit more complicated, as well as the RA, the read A enabled control pulse, and then also associated with the RSC for if we're reading it out as an addressable memory. So there are basically two ways or two kind of sources of data if we're going to bring data into the A register. So one is just so it basically normally retains information between the execution of additional instructions. This is accomplished by sort of the WAG. So this is kind of the WA or normal kind of write pulse, which just brings or gates in information from the write line. So WL01 to WL16. This is like most of the other registers we've seen. It just, whatever data is on the write lines, it'll load that into the A register. Now we also have this WALS, WALS control pulse. And this is used during multiplications. And this kind of enables some of the multiplication to be done just by using it kind of as a shift register. So whenever you're in kind of using binary, you can effectively multiply any value in your register, multiply it by 2 by shifting it to the left. So every time you shift it up, it's the equivalent of multiplying it by 2. So if we apply this kind of WALS pulse, um, rather than loading the data just directly off the right line 01 to right line 016, we do this kind of slight different loading. So rather than WL01 going into bit 1 of our A register, we actually load in the contents of right line 3. And right line 4 goes into 2 and 5 and 6 and so on and so forth. So that is kind of how we do multiplication. Now, this WALS pulse is used for both the A register, and it'll also be used by the L register in order to load data into it slightly differently. And you can see sort of through the description of the WALS control pulse that basically it'll clear the register A and then write those contents in the way that we've kind of specified. And it also makes there's a few just beyond this pure kind of table structure here where they have G16 being written into the contents of A15 and A16. There's also a little bit of this, if if bit position 1 of register G contains a logic 0, then the contents of bit position 16 of register G is entered into position 1. So that's kind of, or sorry, into positions 15 and 16, which is what we see here. If bit position 1 of register G contains a logic 1, then the content of output gate U16 from the adder is entered into bit positions 16 and 15. So if G1 contains a 1, this will actually be U16 instead of G16 for these 2 bits. And then we've also have a few cases of clear bits 14 and 13 of register L and do a few other things. We'll more cover that when we talk about the L register. Another sort of control pulse that we need to be aware of that's related to the A register is the A2X, which is basically take data from A and take it to X. So this is where we have basically enter bits 16 through 1 of register A directly. So not to the right line. So this isn't pushing the right line or the data on the right from the A register onto the right lines and then the X register picking them up from the right lines. It's actually writing it directly into the X register. So as we design this, we have to basically make a provision that there needs to be a direct connection between the A register and the X register to facilitate this specific transfer beyond the central bus. So that's, again, something we need to kind of factor in. So let's kind of look a little bit at this from a kind of, a layout and circuitry of the A register and how we've designed it. And we'll come back to this kind of more complicated components here just in a moment. But a lot of the kind of the core where we do the WA pulse and the XB0, which is our signal for memory address 0, and our WSC. Again, we've got some control logic here that generates our write pulse to load that into our kind of D registers. So this is actually how we would determine when we write data into that particular register. And then what we've used is a bunch of 74LS157s, which are quad, basically 2 input selectors that where we can basically use those 2 kind of write line options. So if we don't have a double, so we have our wall signal, which is corn, we assert it as a 0. So when it goes low, because it's negative logic. So basically we'll say, hey, if walls goes 0, we invert it, so it becomes a 1, and then that goes to our select line, which is okay. If we then go select, our select input is 1, which means we basically select input 2, which is kind of our shifted version of the write lines. If walls is 1, meaning it's not asserted, we invert this, it's a 0. And so we pick our kind of first input in the selector to be able to write our, just one WL1 goes into bit 1, WL2 goes into bit 2, and so on and so forth. And then a little bit further down, because we have that scenario based on the contents of G1, we use an additional selector here to determine, at least for bits 15 and 16, do we use G16 or do we use U16 based on the contents of G1? So that's going to provide, okay, how do we write the data that we want into our registers that's going to store it? And then we provide that little provision here where we've got basically whatever the contents of our A register are, we're going to make it available. And this is where we can connect it to the X register to provide that direct transfer. So that part is fairly straightforward. It's very similar to some of the other registers that we've designed. Where things start getting a little kind of more complicated is, and this is, and I'll actually kind of go to here, is, so we started looking at this kind of table in the last episode, and this kind of maps the sub instructions to the various control pulses that need to be executed in order to provide that particular sub instruction functionality. Now I noticed, and this is something I bumped into when I first started, kind of designing the EEPROM that I'm going to use to kind of translate the machine instructions. So basically, both the sequence contents of the sequence register, the contents of the stage register, so that we know what stage we're in, what the instruction is, and then where we are in our sort of action sequence. So the 12 kind of timing signals that we use for a particular set of sub instructions is okay. So I started kind of coding all of the logic to say, okay, well, if the address of that EEPROM is associated with a combination of these values, and we also bring in the branch of a value, the contents of the branch register, and we'll have a whole video. We'll talk about the EEPROM and how we've kind of designed that out. But as I started kind of doing the coding and putting generating the contents of what's going to go in that register, I noticed that there are these kind of weird couple of cases, and there are I think 5 or 6 of them, 6 of them in total, where you'll notice that there is 2 read pulses at the same time. And that to me, that didn't make sense, because you can only read data out onto the bus. Only, one register can only push data out onto the bus at a time, right? If 2 registers try to push their data out onto the bus at the same time, you get bus contention, right? Because which content should be on the bus? In this case, should it be RC that should be on the bus, or should it be RA on the bus? And so when you want to write that data into the contents of the Y register, or sorry, read that data into the Y register, it's like, well, what contents are we loading into the Y register? Are we loading the contents of the C register, or are we loading the contents of the A register? So I'm like, okay, I'm going to have to figure out why that's the case, because that to me, at first I thought it was just a typo, right? That okay, maybe there was an error when they transcribed this table, but I've of course I found the table in a couple of different places and it was the same. And then I also noticed that there were a few others. So here we have for this MSK or mask instruction, we've got these kind of 2 reads at the same time. For this RN, so these are some channel instructions that basically are used to help manage some of the I/O. Oh, we've got an RC and an RU at the same time. And then we also have these others. We've got the WN, we've got ROR, we've got WOR, and we've got R XOR. So at least for these, you can see these are all with the RU, and this is the RA, right? So it's like, okay, so how do we read out data from the A register at the same time as reading out data from the C register. And this is where I had to go in and look at the contents of the instructions themselves. So we can say, okay, at least these are the two that we need to worry about for the A register, right? Because this is the RA, RC, and this is these ones are RU. So this is kind of the contents of the RU register. So we'll have to factor that in when we build the adder. So the RU, there actually is no U register. It's the output of our sum. So the U in sum from our adders. So that's adding the X and Y registers together. So that'll be a future topic when we get to those. But if I looked at these two particular instructions, you can sort of see it's mask with K. So we basically do a logical AND of the contents of the accumulator with the contents of K. So this is, whatever particular, memory address data that we've kind of loaded. And if you actually look at the way these control pulses work, so for example, in mask, there's a bunch of stuff where we can, load things off of the G register, but really the trick is we're going to load data into the B register, right? Because this is the G register is kind of our memory address. This is actually where we load the data from memory. So basically, we get the G register, and then we eventually take the contents of that G register, move it to our B register, and I mean, like all along the way, we're doing other things. But then we basically take the contents of the C register, which is the inversion of the contents of our B register, our complement, and then we're supposed to AND it with the contents of our A register, and then write that into our Y register. So the way that I kind of had to think about that then, and the OR XOR is very similar. Instead of doing a logical AND, we're doing a logical exclusive OR. So that made things a little bit more complicated from a timing perspective. And this is, like, we talked a little bit about the clock in our last episode of how we generated our kind of our write timer and our read timer. So in order to get this mask instruction to work properly and make sure that we avoid contention on the bus, basically what we have to do is we have to kind of sequence how and when we read data and when we write data and when we perform this logical operation. So instead, we had to kind of change the way that when should we, in this specific set of circumstances, what we need to do is we need to almost do kind of two things at the same time. Instead of just doing one big kind of read time where we put data onto the bus, we need to have this kind of smaller portion or sort of subset of the read timer where sorry. Let's erase this so that we can see it a bit better, is we want to basically read the contents of that BC register onto the bus. So basically, we now have the contents of that C register. We want to perform the logical operation with the A register. So we want to AND whatever the contents of that bus are with our A register contents. And then we want to basically kind of temporarily store that product. So we're going to basically latch and hold that data. And then we're going to have a slightly different pulse of saying, okay, we now need to read that data, that A data, which is kind of this new kind of the results. So it's the ANDed information of what was on the B with what was in A. So we're going to latch and hold that data. And then that data, we're going to read it out onto the bus so that when our write pulse takes place, we can then write our newly ANDed data wherever it needs to go. So in this case, it would go in some instructions would actually go back into A, and in some instructions would actually go to the Y register. So you kind of almost have to think through. It's like, okay, instead of just one big right pulse, we actually have two kind of subsets of right pulse, sort of bring part of the operand together for the anding, combine it with the second operand, and then um, hold that data so that it can then be loaded into whatever register is the destination. So that basically required me to create a little bit more kind of different timing pulses, as well as understanding like, well, when do we need to do these certain things, right? So one is to kind of delay read timing on the A register so that we don't load in the data that we haven't done the logical operation on. There's going to be some similar logic you saw from these cases. We're going to have to do the same thing for the U, or the summer, which we'll talk about when we get into the X register. Um, and then we also need to kind of like pull forward the read timing for the B and C register in certain circumstances. And so this was where I had to actually go back and rework my B/C register a little bit so that this kind of read timing will actually it'll accommodate this kind of scenario of, you know what, sometimes I should only push the contents of the B/C register onto the bus for this very short period of time, in order to facilitate these logical operations. So how does that kind of look in a kind of the electronics? So here I have, and I'm using a 74LS181, which is basically an ALU. And I kind of went back and forth to say, well, should I just use an AND gate and a combination of AND gates and exclusive OR gates in order to kind of provide those two logical operations that we need for the A register. And very quickly, because we're dealing with 16 bits, that means you need to have, 16 AND gates or 16, XOR gates. You can get them in a quad package, so that's 4 chips. But then you need to add additional logic to say, well, when do we AND, when do we exclusive or when do we do other potential operations on the bus? So just from a chip count, it was actually a little bit more economical to just go with 4 of these ALU chips. And basically we have 2 sets of inputs. We have the A input and then the B input. So these are kind of our operands. So one of them is our source from our A register. And then our second source is going to be the contents of the write lines. And this bus data is, so when we do our kind of this particular sequence, is we're going to have a case of that there's data in the A register that we've loaded using either our direct address or our WA pulse. So that's going to be stored here, and that'll be available on these lines. And then we do kind of that early read on the contents of our C register in this case. So that will be now available on our write lines. So we have our second operand. We'll perform our logical operation, and then that output will be available on this F0 through F3. And normally, what we would do is we'd have our bus transceiver, which would just push that data onto the bus whenever we want it or not. However, in this case, we actually need to kind of temporarily store the contents because we want to be able to, if any of these change. So, for example, we pulled our data forward, our read C forward, so that we could put that data onto the bus. But the moment we say, okay, we need to clear the bus so that we can write these contents to wherever they need to go, if we didn't have some way of storing it, if we basically just said, okay, our C pulse ends, that means our bus would clear because the transceiver on the C register would basically go into its kind of floating state. So there would be no data on the bus, and then suddenly because this is not latched, the ALU will perform whatever instructions are based on the data on its inputs. So the moment this data went away, our output would go away as well. So what we have to do is we have to kind of latch the data and kind of store it so that we can actually push that onto the right lines so it can then be picked up by whatever register needs to kind of source that data. So that's kind of the logic of how we've kind of laid it out. And so in order to do that, we need to kind of pick the right functionality for this ALU to perform. So in the case of the A register, we have the AND scenario. So in the case of a mask instruction, we have to do AND. If we get that kind of R XOR instruction, we have to do an exclusive OR. And that's kind of what this logic does here. So basically, we'll look at the control pulses that are being asserted. So between RC, WG, WY, and RA, we will determine which of the two instructions are we performing. So basically what we do is we say, hey, if we see RC, RA, and WY asserted at the same time, well, that's a mask instruction. We need to perform a logical AND. If we see WA, or sorry, RA, RC, and WG at the same time, then it's an R XOR instruction. So we have to do a logical, or sorry, exclusive OR. And we can quickly look at the data sheets this is for the ALU chip. And there's kind of two sets of instructions. So this one here is active low data. So if we were using on the data bus data being active low, we would use kind of these, and it'll say here are the logic functions. It can also do arithmetic operations, but we're not going to use that for our purposes. In the case of while the control pulses in the AGC are active low, the data that we're actually storing in the registers is active high. So the data that's actually stored in a register, if it's a 1, it's a 1. If it's a 0, it's a 0. So that's kind of, so in this case, we actually have to scroll down a little bit to this table, which is active high data. And then we can see the instructions that we need for both ANDs and exclusive ORs. And so what the selection bits need to be. And then we also have the scenario where we need to have just a pass through, because if we don't have either of those instructions, we don't want the ALU to do anything. We just want it to pass the data from A right through with no manipulation at all. So that kind of gives us the logic of basically what bits we need to set on the selector side, and that's kind of right here where we generate the logic to set S0, S1, S2, and S3, which you can see is a little decoder, which is basically provides the instruction of, well, what do we want the ALU to do? And so we can, there's some other stuff that we don't need to worry about. That's more for if we're going to use some of the arithmetic functions that we're just going to ignore. The other part just kind of comes back up to here, which is basically some of the additional logic that I had to put in to create the appropriate blocking for that kind of delayed write time, so that basically rather than just reading the data onto the bus from the A register, we want to delay that so we have time for the C register to push the data, the ALU to perform its logical function, and then once all that's done, then we can read the contents of the A register back out onto the bus. And if it's one of these scenarios where we have one of those two instructions, we'll perform the logical operation. If we don't have those kind of sequence of control pulses, then we're executing something else. And so we can just pass it through. We don't have to worry about bringing in data and doing the logical operation. We just pass the data right onto the bus. So these are basically some of the ANDing of different, from our 4 megahertz clock, our clock 1 signal, our RT clock, and then even actually our 8-bit signal here, 8 megahertz signal here, that are all kind of ANDed together to create the clocking that we need for both the read as well as the latching, so that we've got this kind of clock here that we use to like when do we want to latch that data and basically hold that data within the 373 chip, so that we can ensure that it's available to be on the bus when we need it. And then the actual basically the right data uh, onto the out of the register. And that's where we kind of get this here, that little delatch signal, uh, kind of signal here is that we push the data from the RC data onto the bus. So this is where we push the contents of C. At that same time, we generate the selection control for the ALU. The ALU will then perform that logical operation with the contents of C and the contents of A. We'll then latch it, so we're kind of storing it. Then the C register control pulse read will be basically the clock will basically say, hey, we don't need to push that data onto the bus anymore, but we've latched it, so we're still holding the data that's available, so that if we need to write that data or read that data anywhere, we've got that data available, even though the contents of the C register are no longer on the bus. So if we look at kind of the bill of materials for the A register, we've got, of course, the 4-bit D registers. So that's the register itself. We've got the D type latch. So this is instead of the octal transceiver, we're using this D type latch so we can store the data and hold it on the bus, so that whoever wants it can pick it up. We've got the 4181 ALUs that we're using. We've got the 5 quad 2-line to 1-line selector chips. And then, of course, all the logic that kind of goes together. So the 2-hex inverter chips, a quad 2-input NOR gate, a quad 2-input AND gate, one try 3-input AND gate, one try 3-input NOR gate, a quad 2-input OR gate chip, and then a buffer for our clock and reset, and then of course the lights and resistors and capacitors for everything to work. And that's kind of, I'm just actually in the process of doing the final wiring up of that board, and then can do the testing. But then I said I had to make a few little changes to my B register, and I'll just quickly pull up the circuitry on that, or the schematic. Is basically the changes is here, where we're using, again, if we have that kind of sequence of logic coming from either the RA or RU, we're going to then generate slightly shifted clock to be able to push that data onto the bus a little bit early compared to the normal scenarios where we've got this little RT here, in order to just have the regular clock for those purposes. And that's basically, we've kind of combined the RC, RB, RA, and RU together to provide kind of that logical selection, and that's generated from the RA, RC, RC, RU. Basically, whenever we have these two reads, control pulses asserted simultaneously, then the B register is going to act slightly differently in when it pushes that data out onto the bus, because we wanted just that short little window at the very beginning so we can push the data on, allow the ALU to pick it up, perform the logical operation, latch it, and then when the appropriate read pulse for that register, whether it's RU in the case of the summer, or the X board, the X register board will build, or whether it's the RA, in this case on the A register board, so that we can now kind of read our new ANDed or XOR or exclusive OR data onto the bus, so that in this case the G bus can, or the G register can pick it up, or in this case the Y register can pick it up. So And this one's been a little bit more, complicated as the registers go. The L register is a little bit simpler. It doesn't have some of this control post logic we need to work out. It has a few other things that make it a little bit interesting. But this will be very similar to what we'll have to do when we build our X register, because that's where our adders are. And so the outputs of the X register are actually this U, which is the outputs of our summers, our adders, in order to produce those particular outputs. So yeah, thanks for joining. Please subscribe. Like I said, I'm going to try to put one of these out every week or so. Next week might be a little bit late. I have a bit of a vacation coming up, so I may not get to it for next weekend. But I should have something in the next week and a bit when we're going to talk a little bit about the L register. Uh, as always, please send me any questions you might have. Point out any errors that you've noticed. Like I'm going through this the first time, so it's always good for folks that have had other experience working on the AGC, whether it's some of the folks that have been involved in restoration or hands-on real AGCs, or the virtual AGC project. Again, always open to feedback, questions, comments, and corrections. Thanks for joining, and we'll talk to you next time.